Well, greetings out there in YouTube land, and welcome to today's big video featuring the scratch building of a single-ended high-wattage amplifier utilizing either KT-88 or a parallel pair of 6L6 GCs. I'm picking up right where we left off, except that I have cleaned up the workshop table here a bit, so let's get started. Now the final step before cleaning up the chassis and preparing it for paint is to rivet in all of the terminal strips. And I ordered the mother load here, all different lengths, and what I have to do now is sit here and kind of visualize what the circuit will be like and figure out where I'm going to need these terminal strips. Now I'm going to put terminal strips here and here. Now bear in mind, this is going to be the switch that controls the cathode bias, whether it's a KT-88 or a pair of 6L6 GCs. So I'm going to have a terminal strip here for those components to be attached to and to communicate with the tubes. Next, I'm going to provide terminal strips for the tone controls, for the volume, and another one here for the two input jacks, and then one here for some of the components that are going to go to the preamp tube, probably a 12AX7. One final change I made was to rotate the output transformer. Before, this was going to be the secondary, which the wires then would have to come all the way up here, and this was going to be the primary, which meant that the wires had to come all the way back here, and that just didn't make sense. So I'm going to reverse it, and the primary wires then will come from the GZ34 and from the filter cap array here into the primary hole here to the output transformer. And look at this, the secondary wires will only have to go from here to each of the output jacks. You can't ask for things to be much neater than that. That's where I stand right now. I'm going to stop and make these changes. I have to drill holes a little larger, drill a couple mounting holes for the fan transformer and things of that sort, maybe some holes here for the terminal strips. I'll be right back when I'm finished. In preparation for priming and painting the chassis, I've bead blasted the exterior surface. I'm going to go through and fill in some little pinholes. I also bead blasted the whole interior surface so that we'll have no problem with electrical contact. I arc welded a ground strap right here for the green wire that's going to come in with the power cord, so there can never be any separation of the chassis and earth ground. And now I think I'm going to pop rivet in all of those terminal strips so that the outside portion of the rivet is painted, and then I think we'll be ready to prime and paint this jewel. You can see that the bead blasting has left a very slightly rough surface for the paint to adhere to. Well, I've riveted in the terminal strips. Not all that many, are there really? I may have to add a few more, but at least these are in. And I'm taping off all the holes so that the paint can't get overspray on the inside or make any runs inside. Okay, so I'm going to finish taping, and then I think we'll be ready for the primer. I've applied a couple coats of a etching primer that should assure good adhesion with the color coat. You can see, I think those corners came out pretty nice. Maybe one more coat for good measure, and then let it dry overnight, and then I'll apply the color coat tomorrow. Okay, I lightly sanded the primer and then applied a couple color coats. I'm using the Gloss Regal Blue from Krylon, which I think is a really pretty deep blue. And once this dries, then I'm going to start spraying clear coat over it so that it'll really be glossy. I use a high gloss automotive clear coat, which should be very tough, resistant to chipping, and really pretty. Well, the color coat dried all night, and it's now totally set up where if you press your thumb against it, you don't get a fingerprint. Now I'm going to spray a couple coats of clear. I'm going to use this Nason Select Clear. It's a catalyzed urethane. Okay, I'm going to mix in a catalyst, and it's going to be absolutely rock hard and just as glossy can be. There's 2 coats of clear, and as you can see, it looks about like blue glass, which is what I was hoping for. Now, if it can just set up without any vultures landing on it and shedding feathers, hopefully it'll sit up nice and hard and quickly, and we can proceed with the assembly procedure, installing our components in our chassis. Here you can get a gander at the control panel. Pretty shiny, eh? I can't help but show off my spray gun kit. It's originally made by DeVilbiss and sold by Eastwood. And as you can see, you've got a regular gun, detail gun, tanks, pressure regulator, different nozzles, all different apertures, and a complete tool kit and cleaning kit. And boy did it work. This is one I used. I used the detail gun and almost a full tank of that catalyzed clear. And as you can see, it cleaned up beautifully. Put it back in, you couldn't even tell it had been used. And I should add that Aunt Doug got me this for Christmas. I picked it out and ordered it, and I used her credit card. And later I told her that she bought me this for Christmas, and she was very happy, I promise. And we can finally begin the assembly process and then the wiring. Well, here we are about 20 hours later, and the paint has completely set up, and also you notice a lot of that orange peel has disappeared as the paint sort of shrank and hardened and adhered to the surface. Okay, so now we're ready to remove the tape that masks the holes and begin assembling our chassis. I've installed the handles. I'm leaving them in sort of a polished silver finish, which I think contrasts just beautifully with the blue paint. I removed all the tape from the masking of the holes and other things inside. And now it's time to start installing the different components that will have to be wired together into a purposeful circuit. Now that handles are installed, I've installed the 4 grommets in preparation to installing the transformers here on top of the chassis. I just couldn't resist pop riveting in the 3 octal tube sockets, and next I will screw in the 12AX7 tube base. Here's the underside view. The power transformer is installed, 3 tube sockets and the 12AX7. Now time to flip it over, and I think we can install the filter choke and then the behemoth output transformer. Here we see the filter choke is installed with its 2 wires going through the grommet, and next will be the massive output transformer and the fan. Well, the 3 transformers are all securely installed. Now it's time for the fan, and then we can work on the rear and front control panels. And the fan has now been installed with the wires to the grommet, so the rear component array is complete, and we can now focus on installing all of the components to the front and rear control panel. Well, I've installed all of the components in the front control panel. Here is the bias resistor selector switch, the pilot light. This is the double pole on-off switch. This will be the voltmeter, the ammeter, bass, treble, volume, and the two inputs from the guitar. And I like to show you things I've done that are wrong so it'll save you from making the same mistake. These should have been closer together. This one here is dangerously close to this edge and actually kind of close to shorting out on that floor screen. So if I were you, I would make these about a ½ inch closer together. Now it's upside down, but here is how the controls are going to look. Now I was going to use those Fender style knobs. I thought, nah, this looks a lot snazzier. I got those backing plates that are numbered. I'm going to use probably blue chicken head knobs, and here's the voltmeter, the ammeter, on-off switch, and the pilot light. And I'll show it to you right side up in a little while, and I've got to go in and make sure everything's perfectly square and all, but that's how it's going to look. Also notice that I put the gauges in from the back instead of from the front. Now some of the viewers had mentioned this would be a good idea, and I agree. I noticed that the diameter of the bezel and the diameter of the inside of the gauge here, the back of it, are the same diameter, so you can put them in either way. But I thought this looked a lot neater, and like I said, you'll get a better look at it when I flip this over and we don't have the glare. Okay, so that's how it is. I'm going to turn it around now and do the rear control panel. The components have all been installed on the rear control panel. I forgot there were 4 output impedances in this output transformer, so I had to order a 4th jack. This will be the NFB control in the middle. There will be no negative feedback. In one position will be a low amount, and the next position will be a medium amount based on different resistances that I will put into the loop. Here is the fuse holder. I'm thinking probably about a 3 amp fuse to protect the circuit, and here is the AC receptacle for the power cord. Pretty nice reflection, eh? And here's an inside view of the front control panel, showing all of the components. You can see that this input jack here is positioned a little too close to the steel fold over here. Like I said, if I had to do over again, they would be closer together, and this would be further from this piece of steel. Now that all the components are installed, it's time to start wiring our circuit, which is always my favorite part. Here's an accident waiting to happen. As you know, tube sockets from underneath are numbered clockwise, beginning immediately to the right of the notch. So this should be 1, this should be 2, this should be 3. Okay, and instead it looks like this is 8, this is 1, and this is 2. The numbering is very misleading. The 1 should be over here, the 2 should be here, the 3 should be here. So in this case you have to ignore the numbers and wire the socket the way you know these sockets are meant to be wired. The wiring's coming along quite well. Here is the black hot wire from the AC power cord, and we see that it is wound tightly around the white return wire. Both of them come up here to the upper poles on the single throw double pole switch. This way, when the switch is disengaged, both the hot wire and the return wire are disconnected from the circuit. Now when the switch is closed, the white return wire here connects to this white wire, twisted, comes down here to this terminal, and it goes to the white lead into the primary of the power transformer. The black lead, when the switch is closed, comes down here to this terminal and then proceeds here, twisted around the return, and comes over to the fuse, to the end of the fuse, and then leaves from the middle terminal here on the fuse and comes over to this terminal where it connects to the black wire for the primary of the power transformer. As is my normal practice, when wiring the primary, will put the switch first and then the fuse, so that when the power switch is off, everything is turned off. The entire circuit is off. Many people prefer to wire the fuse first and then go to the switch. I'll leave it up to you. Whichever you prefer, do it that way. Now, when the switch is closed, the primary of the power transformer will be energized. Notice also that there are two red wires here connected to the black and white incoming AC wires. They come over here to the fan step-down transformer. That's the primary. The red wires are the primary, the 120 volt primary winding. Then the yellow 12 volt wires come over here, where they then engage a full wave bridge rectifier, with the positive lead going to the positive lead of the ventilation fan and the negative lead going to the negative terminal on the fan. Now, when the power switch is closed, not only is the power transformer energized, but also the fan will start. Now, looking at the wiring of the rectifier, we see here that pins 4 and 6 of the socket receive the high voltage secondary winding output wires, and the center tap, which is red with a yellow band, goes right here to the central terminal, which is grounded. The 5 volt output from the power transformer goes to pin 2 and pin 8 of the rectifier socket. Longtime viewers will recall my frequent jests over Underwriter Laboratory stickers being placed on Death Trap series filament amplifiers. Well, a viewer took it to heart and prepared some special ones. In this case, instead of UL for Underwriter Laboratories, we have UD for, yep, your old Uncle Doug. And I really appreciate it. I'm going to cut these out and put them on my recently built amplifiers, and I just wanted to express my appreciation for their cleverness and share this with you all. And here's our Uncle Doug sticker on the back of the recently completed Vibrachamp Reverb. Definitely the finishing touch it needed. And I will be placing a sticker on the rear of the Brothel Inspector robot amp that I built several years ago. Once again, viewers that have been with me a while will remember all the time and effort that went into this jewel. Where else are you going to get a robot with steampunk controls and bubbler Christmas light eyes? And here you see the rear of the robot cabinet with the danger high voltage warning label and the Uncle Doug electrical safety sticker. And for the longtime viewers that recall the blue Art Deco amp that I built out of steel several years ago, it was the first one that I ever put a cooling fan into. We're going to turn it around and put on our Uncle Doug sticker. And here we swoop into the rear of the cabinet. We see the Fender 5F11 Vibrolux chassis lurking within. And there's the mighty Uncle Doug sticker, proudly proclaiming that electrical safety is contained within. I should mention that the fellow who made these stickers sent them all the way from Canada, and we sure appreciate his efforts. I thought you'd get a kick out of this. So thanks, Vince. You really made my day. Now let's get back to work on our video. Let's review the wiring that's been completed up to this point. We're going to take our B plus from pin 8 of the rectifier, and we'll come up here to a four-way junction. One lead will go to the reservoir capacitors in series. One will come up here to the primary of the output transformer, and one lead will go over here to the filter. Here we see the B plus exiting from pin 8 of the rectifier. It comes over here to this terminal, and this is where the four-way split will take place. One lead comes over here to the reservoir capacitors. We see that they are in series. We have a 70 at 350 and a 70 at 350. In series, that's going to give us 35 microfarads at 700 volts. Each of them is strapped with a 220 k ohm resistor to ensure that the voltage is divided evenly between them. We see that they are grounded here to this terminal of the terminal strip. It's the one riveted to the chassis. Here's our next lead coming away from the four-way terminal, and it goes to the primary of the output transformer. And finally, the black lead here, which comes down to the filter choke. So that completes the first stage of wiring of our power rail. Next, we'll pick up where the B plus exits from the filter choke, and we'll go to a 20 microfarad filter cap, and then through a resistor of unknown value at the moment to the screen of the output tube. Here we see the wire coming out of the filter choke. It comes over here and it goes through the blue wire to connect to the 20 microfarad electrolytic filter cap, which is grounded at this end. I've come here to this terminal because I'm going to place a resistor between here and the screen of the output tube or tubes so that I can reduce the screen voltage to an appropriate level. The value of that resistor will have to be determined experimentally. I can calculate pretty close, but then I'll have to fine-tune it. Then that will happen once the circuit is functional. Then finally, the third capacitor resistor node. I take it here from the capacitor. The resistor, I do not know the value yet, but it will jump from here to here. I'll figure that out once the circuit is working, but I bring the B plus over here and deliver it through two 100K resistors to the plates of the 12 AX7 preamp tube. I finished wiring the two gauges. You see the brown wire right here that comes from the primary of the output transformer. Runs through the ammeter and then through this blue wire down here to pin 3, which is the plate of this KT-88 socket. Then from the plate, we'll run up here through this blue wire to one side of the voltmeter, and then through the other side of the voltmeter to pin 8, which is the cathode of the KT-88 socket. Therefore, we will have a reading of the plate current and the net plate voltage between the plate and the cathode of whatever tube is plugged into this socket. Then, when I connect the two tube plates with this yellow wire, I will get a reading in milliamps of the plate current of either the KT-88 if it's in this socket, or both 6L6s if they're in both sockets. Let's take a few moments out from our wiring extravaganza to Mitzi, please. Mitzi, let's take a few moments out from our wiring extravaganza to have today's episode of Jack's Geek Fest. There seemed to be a lot of enthusiasm in the comments to part 1 about the meters that I was incorporating into this circuit. So let's take a few moments to discuss them, how they fit into the circuit, and what impact they'll have upon it. Here's a simplified diagram of a single output tube. In this case would be the KT-88. However, since the two tube sockets are wired in parallel, everything I say here would apply to the two 606 GCs if they were in both of the tube sockets. And here we see the milliammeter is in series within the B+ supply that passes through the primary winding of the output transformer to the plate of the output tube or tubes. Now there's two things about this meter that we have to know. Number one, does it have DC resistance? And I'm glad to report that it does not. But if it did, it would cause two problems. Number one, it would reduce the plate voltage. And number two, because it had a resistance to the flow of current, it would develop heat, which could ultimately damage the meter. So when I measured it very carefully, I found that it has absolutely no resistance whatsoever. So we can rule out the two possible issues that it could cause. Therefore, I'm just going to wire it in series in the B+ line to the plate. And the advantage of that is I will get true plate current on this meter, because if I connected down here through the cathode, I would get both plate and screen current. But since I'm going to the plate itself, I will get the net plate current, which is what we'll use to calculate our plate dissipation and set the bias for our tube. The next meter I'm going to install will be the voltmeter, and it will be placed logically enough between the plate and the cathode to give us net plate voltage. By net, I mean when you have cathode bias, if you measure the voltage between the plate and ground, you will add in the voltage drop across the bias resistor and get a falsely elevated value. So the only accurate value for plate voltage then with cathode bias is to measure between the plate and the cathode. Well, that's fine enough, but does this meter, by its presence, alter the relationship between the plate and the cathode? Let's see. What if our voltmeter had no resistance, just like the ammeter? Well, wouldn't we have a dead short? Okay, why would any of the electrons waste their time traveling through the internal resistance of the tube when they could just take a shortcut? So, zero resistance will not work here, whereas it's essential in the ammeter case. So what we want really with any type of a voltmeter is the highest possible resistance you can get, because we want no current to flow through it and we want no voltage drop to occur across it. Now, infinite resistance is very difficult with a voltmeter. They won't work. Well, this type won't work with infinite resistance. Instead, it's pretty close. I measured it, and it is 500,000 ohms. Now, I have to go to handheld here because I'm going to have to move the camera around a little. Let's say we start off with 420 DC volts in our power supply at this node. As it comes up here toward our plate, it'll pass through the primary of the output transformer and encounter 57 ohms of DC resistance. That will cause a voltage drop of about 5 volts, so I estimate our plate voltage at around 415 volts DC. Now, using Ohm's law, the current flow through the meter will be the voltage, which we said was 415 volts, divided by the resistance, which is 500,000. And it turns out that 0.8 milliamps of current is going to flow through the voltmeter and bypass the tube. Okay, is that an issue to us? Okay, well, remember we said that our plate current is going to be around between like 85 to 100 milliamps. That means that the bypassing current that will go through our meter will be less than 1%. In other words, I think probably an error that we can just forget about, ignore. Now there's a second issue, is how hot is the meter going to get? Well, let's see what the power derived within it is by the flow of 0.8 milliamps through a resistance of 500,000 ohms. And we square the current flow and multiply it times the resistance, and it's 0.3 watts. Now you saw the size of the meter. It will have no trouble dissipating that much heat. So what I'm going to come down to here on this, in my opinion, we can ignore the current that bypasses through the voltmeter, and we can ignore the heat that will be developed within it. But I hope this shows you something. First off, the importance of Ohm's laws. Secondly, that you can't just start tacking different components into a circuit without them affecting the circuit. So you need to calculate the effect they'll have and see if it's something you can live with. In this case, we can. You know, while I have the diagram here, let me go over one other thing. I sort of glossed over when we were looking in at the wiring over how I got the value for that screen voltage dropping resistor. I said 33K. Let me show you how I got it. Okay, I figured 420 volts going through the filter choke with a DC resistance at 211 ohms is going to leave me around 418 volts in my rail. Okay, now if I want to drop 198 volts, which will leave me 220 in my screen, I'm going to use Ohm's law to tell me how much resistance is required to drop 198 volts from 418 down to 220, and I figure my screen resistance is going to be around 6 milliamps. It can go a little higher, but that's going to be if the amp's running wide open, and I don't anticipate that. Okay, so we're going to use 6 milliamps of current flow and a desired voltage drop of 198 volts. Now, here are all of my calculations that I made in this circuit to see what values of resistors I needed and things like that. I'm giving you an example here of one of them. I think would put you all to sleep if I went through everything, but let's look at this one. Remember we said that we wanted 198 volts dropped, and we have 0.006 amps or 6 milliamps of current flow. When you divide, you get 33K. Therefore, I installed a 33K resistor right here to give me the desired voltage drop so that my screen would be around 220, which is the recommended value for KT-88. One other consideration for that resistor is what power rating should it be? We know that power is equal to current squared times resistance. Okay, I'm running 0.006 amps, I square it, and we're looking at 33K resistance, and that results in 1.2 watts of heat. Normally you will double this, so I'm thinking around 2 watts, maybe 3 watts would be correct for our 33K, and here you see 2 watt voltage dropping resistor to our screens. For you masochists out there, let's discuss briefly how I came up with a cathode bias resistor value. The bias resistor is bias volts divided by cathode current. Now, looking at research and all on a KT-88 in this circuit, I found it to be around minus 39 volts. That seems high to me, but I'm going to go with that just to play it safe. And we'll divide by the cathode current. Now that's both the plate current and the screen current. So let's figure it's 0.091 amps. Okay, when you do the division, you end up with 429 ohms. I thought, why not play it safe and go for 500? I can always bring it down. What you don't want to do is start off with a very low value and roast your tube before you get a chance to correct the cathode bias. So I'm going to start out with 500 ohms and hope for the best. Now let's look at the power rating of the cathode bias resistor. We know that power is going to equal the cathode current squared times the resistance of the bias resistor that will be installed, and we end up with 4.14 watts. Let's double it and round it off. So 10 watts would probably be adequate. Why, as you will see, did I use 20? Well, very simple reason. I didn't have another 500 ohm 10 watt resistor. I did have two 1000s, so I put them in parallel to get 500 ohms and was forced to accept then 20 watts. So if I end up with like 5 times the power rating that I need, so what? What I'll do later is probably order, when I get a chance, a 500 ohm 10 watt resistor and replace the 2000s that are in parallel. Okay, your suffering is over. The math lesson's done. Let's get back to work. I started wiring the 6.3 volt filament supply. You see the twisted wires coming over here to the pilot light lugs, where I have attached the, in this case, 110 ohm resistors to each lug to create a virtual center tap. For some reason, the 6.3 volt supply here has no center tap, so I made one using these resistors, and then I continue from those lugs twisted down here to pin 2 and 7 on the KT-88 socket. I'll then jumper over here to the parallel 6L6 socket, and then come over here finally to the 12AX7 socket. It's been a busy day wiring. Let's review what's been done. We start here with the third node electrolytic capacitor, and we see the blue wire that comes along here and goes over to the preamp tube. We see that it feeds the two plates through 100K plate resistors. That'll be pin 1 and pin 6. Then we'll have the output from the plate, which will come up here through a 0.02 microfarad cap. And then we have our 220K bleeder between the grid of the output tubes and ground, so that our grids do not become saturated with electrons. And we continue on here where we feed the grids of the two output tubes if they are 6L6GCs, or the one output tube if it's a KT-88. And the grids are fed through grid blocker resistors, which are as close as possible to the pins associated with the grid in each of the tubes. It should be noted that the value that I selected for the two grid blockers is 1.5K, which is the standard used on all Fender amplifiers. And we also see that the signal then is fed not only to the left-hand output tube, but then through the red wire to the right-hand output tube, which also has a grid blocker resistor. Next, let's trace the screen supply. We'll start here with the second electrolytic capacitor, and we see the blue wire leaving, and it comes around right here, and then it feeds through a 33K resistor. Now I've calculated that that will bring the about 425 volts of B plus down to around 225, and then through screen resistors in here to the screen pins on each of the output tubes. Again, I'm using Fender values, so these are 470 ohm screen resistor. I had to flip the chassis over so I could tighten this circular nut on the bias selector switch, which I just received today, and I had forgotten how neat this looked. I was able to install the navy blue chicken heads. You can see how the two gauges look without those big square frames showing. All the big transformers, the fan. I really am getting enthusiastic about this. I think it looks really snazzy, very kind of industrial, and I just hope it sounds as good as it looks. Okay, time to get back to work. Well, I've done quite a bit of wiring, and now it's time to review what's been done. First off here is the bias selector switch. You notice that the middle lug is connected to pin 8 of both tube sockets, which is the cathode. Now when the toggle is flipped so that it closes this contact here, we'll follow this out, and we come over here to 500 ohms, 10 watt for a bias resistor, and 47 microfarads at 160 volts for the cathode bypass cap. These are pretty husky, okay, but I think these are going to be suitable for the 6L6s in parallel. So when those tubes are installed in the sockets, I'll make sure that the toggle is flipped to close these two contacts. Now when the KT-88 is installed, and it's kind of interesting, but it can be installed in either socket, I'll probably stick with this socket here, then I will flip the toggle switch the other way so that it closes the middle and left-hand contact, and we will then connect to this biasing setup here, in which you see we have two 1000 ohm ballast resistors, 10 watts each. They're in parallel, so we have here 500 ohms at 20 watts of cathode bias resistance. We also have two 100 microfarad caps in parallel for 200 microfarads at 160 volts of cathode bypass capacitance. This, I understand, is appropriate for KT-88. No doubt, after I've got this up and running, I may have to fine-tune this resistance and this resistance, but we'll wait until that time and then do the fine-tuning, and I of course will amend the schematic to reflect the optimum values that I come up with. You can see that now that both of the octal tube bases are fully wired, I went ahead and did the 6.3 volt filament supply in here to pins 7 and pins 2, and then I also have continued it here, and I will install it as the last wiring process on the 12AX7 tube base. I like to wait till last on the filament wiring because it gives you the room and space so that you can go in here, do all your wiring, and then just bring this in from up above and wire it. It just seems easier to me. Now let's take a look at the switchable NFB. We see a wire coming in here from the 32 ohm socket from our output transformer, and it goes to the middle terminal. Then, depending on which way the toggle switch is flipped, we either have 2200 ohms of NFB resistance, 5600 ohms, or if the toggle is in the middle position, we have no negative feedback whatsoever. Also, I did a shielded cable taking that NFB over here to the cathode of the 12AX7. It just seemed to me like that was asking for some sort of hum or interference, so I shielded it. And here we have Mitzi Cat basking in the sun on the kitchen table. What a fact. Oh, that was the bird noise that she makes when she sees doves in the backyard. Mitzi and I will go inside to show you our next project. Are you ready to go in, Mitzi? Yep. I'm looking everywhere for Jack and I can't find him. Jack, are you here in the bathroom? No, I guess not. Whenever I'm doing a layout like this for an amp, I always focus on isolating the preamp section from the rest of the circuit. But sometimes that leads me to make what I think might be a tactical error, and that is, look right here, I've got AC going into this transformer right next to the NFB switch. Now, I don't know how sensitive this would be to the presence of the 60 cycle right here or this transformer, but I really can't move the transformer anywhere at this stage of the game. So what I'm going to do is create a metal shield here to sort of insulate the transformer's electrical field from the NFB switch, just in the anticipation that it might cause some hum. And while I'm at it, I'm not thrilled with the way I routed the filter choke leads. It made sense early on, but now that this has become so populated, I'm going to reroute them this way and make shorter runs and away from harm's way, hopefully, in the form of that transformer and the AC wiring going to the rectifier. I have shortened and rerouted the filter choke wires so they're nowhere near this AC field, and I've also rerouted the 120 volt AC feed to the fan transformer. I've taken it away from this area and tightly wrapped it and then brought it down this way. Now I'm going to make a shield that will extend between the transformer and the NFB switch. Step one is to make a cardboard template of the shield. This tab here will be the way that it is mounted. It'll be under the nut at the other end of that screw. Now I'm going to lay it out flat and transfer the shape to a piece of sheet metal, and then I'll cut it out. Well, fortunately I had an old panel from a Ream air conditioner heater that was replaced. I cut out some of the sheet metal and I've made the shield, and now I've got to make the slot for the installation bracket, and then I think we'll be ready to install this beast. So here's the finished shield. You can see that tab there that's going to fit right under this nut and lock washer and hold it in place. Let me install it and then I'll show it to you. And there is the shield installed with that one screw holding the slotted tab. You see that it completely shields the NFB switch and the resistors, and it's cut away so that it doesn't endanger any energized wires. So I think we're in pretty good shape. Plus, the heat is welcome to rise and come out of it as it sees fit. And because I was careful with the cutting and bending, I end up with a really nice enamel paint job. I'm almost finished with the wiring of the Preamp 12AX7. As you can see from pin 3 and pin 8, we have our cathode bias resistors and bypass caps in place. I've also wired the 2 input jacks, and as I previously reported, some concern with a possible short between the jack and this close steel shelf here. I was able to kind of bend the lugs in and rotate this so that contact is extremely unlikely. But still, I put several layers of electrical tape underneath the shelf, so even if this did happen to rotate a little, it could not make a grounding contact. Then the signal from the input jacks is shielded and comes over here to pin 2, which is the grid of the first triode of our preamp tube, but probably a 12AX7. The treble control and bass control have both been wired according to the standard Fender 2-control tone stack diagram, with shielded cables wherever possible. Then our pre-amplified signal will exit from the plate of the second triode of the preamp tube through this yellow wire, through a 0.02 microfarad coupling cap, down here to the red wire, which carries it over to the grid or grids of the output tubes. And here is the 220K bleed-off resistor, whose deletion from the preliminary schematic in the Part 1 video caused such consternation. We see here that it's happily in place, and its purpose is to prevent an accumulation of electrons on the grids of our output tubes from blocking our signal. This will allow those excess electrons to go to ground. Now, one of our final wiring steps will be to connect the 6.3 volt filament supply to pins 4 and 5 and pin 9 of our preamp tube. And there, with that final soldering of our 6.3 volt supply to our preamp tube, we're pretty well finished with the wiring. A couple small additional details, and that'll be to calculate the proper resistance for the step-down resistor here for between node 2 and node 3. And I'm not thrilled with this carbon comp resistor in this rather critical position. I'll probably order a better ballast resistor of higher wattage and replace it. Also, I'm not thrilled that I had to do the shield here over this transformer. In retrospect, it should have been on top of the chassis on the other side of this surface. Right back here, there's probably room for it, and then just have the wires come through a grommeted hole rather than mount it back here. Okay, I tell you these things to save you. If you're going to try to build one of these, I'm trying to save you from any pitfalls that I didn't avoid so that you can. As you all know, I'm a big fan of shielded cable. And shielded cable is not that easy to come by, and I really like this type that has the woven shield, sort of like a Chinese handcuff, around the outside of the insulated wire. And let me show you my new method of doing this. Okay, it's a little simpler than the old way of trying to strip and separate the filaments and all that. Let me show you. I found this shield material on eBay. It arrives flat, okay, and it comes in different widths, but then it opens up inside like a straw, and you slide the wire inside of it and turn your regular wire into shielded cable, and you slide in as much as you want, and then cut and then push the wire a little further out, strip both ends, and I usually take a little of the slack, twist it for my ground. But like I said, you can buy this stuff on eBay now. I got the 1/8 inch, and I thought that would be just perfect for my signal wires. To be honest, this stuff's really hard to work with. I've wasted a bunch of it. I would get the 1/4 inch width if you're going to give this a try. I think it'd be a lot easier for you to work with. But anyway, like you see, you just slide in the wires, and if it starts to back up or block where it won't protrude or go any further, you just do the old Chinese handcuff and kind of open it up a little bit, and then you can push it further in. Okay, so that's the new technique. You might like it, you might hate it, but at least it's something different and an easy way to turn any wire you've got of the right gauge into shielded cable. Well, a couple final wiring chores. I decided on 10K here for this internodal resistor, and I've decided that this red wire here needs to be shielded. Might as well if it's going to the grids of the output tubes. So I'm going to replace that with a shielded wire. Here's the shielded cable that I'm going to replace that red wire with. I find that using solid wire rather than multi-stranded, it's easier to push through. It's just more rigid. Also, a little bit of heat shrink right here will keep those loose cut ends of the shield from fraying. Okay, there's a learning curve on this, and once you kind of get used to it, you can produce these shielded cables in very short order. I put an expendable tube set into the amp to test it. That's a 5U4, a couple of 5881s. I didn't want to jeopardize you know, a brand new or expensive set of tubes, and I was getting kind of intermittent volume, and I noticed that the base of the 12AX7 is completely separated here from the rest of the tube base, so that the pins don't even hardly make contact, which means now I have the delightful task of completely rewiring the 12AX7 tube base with a decent piece of equipment rather than this piece of trash. So I'll be back shortly after the work is done. Well, I got all the leads unsoldered and went to lift up on the base, and the whole tail part of it with the little connection sockets just came loose. So when you're pushing the tube in, instead of the pins going into the little sockets, the whole thing just pushes up. What a piece of junk. I'm disgusted. I'm going to go look up the part number on this, and I'm going to warn you so that you never order one of these. And meanwhile, I'm going to install a better quality one and then rewire the socket. Well, I got the tube socket out, and the problem is obvious. Here is a properly manufactured tube socket, and you see that this little pipe right here is splayed over essentially to rivet the rear to the top of the socket. And in this case, as you can see, no attempt was ever made to splay that, so the back was never really attached to the front. Total disaster. I'll still give you the part number of this so you can avoid these. God knows how many more bad ones there are in the bin. Okay, meanwhile, I'm going to install a properly manufactured tube socket. You're probably not going to believe this, but the only 12AX7 tube base that I have, and I've got a bunch of these, is larger diameter than the hole that was drilled for that lousy one that fell apart. So now I'm having to go back to a essentially finished amplifier and hog out a larger hole for the tube base, and that doesn't do much for my nervous system, I'll tell you. Well, the new 12AX7 socket is installed. Now I have to flip this jewel over and wire it. Well, the 12AX7 tube base now has been completely rewired, and just to add to my misery, the rotation was different on this socket than it was on the original, so all of the leads and wires that were cut to perfect length no longer reached. So it had to be extensively rewired, which was no fun at all. But it's done. Let's flip it back over, put in some tubes, and see if we have any noise. Of the good type, I hope. Okay, all the wiring is finished. Now it's time to plug in some tubes and see if our circuit is operational. For initial testing purposes, I'm going to put in a pair of 5881s and a 5U4 rectifier. Okay, I don't want to put in expensive or hard to replace tubes yet. I want to just do some basic testing of the circuit with these tubes in place, and they are expendable if anything does go wrong. I've connected voltmeters to the plate of the 12AX7 and to the screen of the KT-88 or 6L6GC sockets. So we can monitor what the voltages are and make sure we don't exceed those that are could be harmful for the tubes. Okay, so first off, I'm going to plug the amp into the dim bulb current limiter and then connect it to the variac and slowly bring the amp up to full operating voltage, and then check our values and see if it's safe to proceed with a good tube set. I'll also be injecting a 300 cycle per second tone into the input jack so that we'll hopefully hear the tone. We can tell how clean it sounds, and also tell if we have any 60 or 120 hertz background hum or noise. We can see here that the pilot light is starting to illuminate. We're also getting some readings here. This is the 12AX7 plate. This is the output tube screen. Let's turn up our volume control a little. There's our 300 cycle per second tone, which sounds crystal clear to me. Let me turn it back down. We'll go over to the speaker a couple inches away. No 60 cycle or 120 cycle hum. And we also see that our output tubes are flowing some current. Bear in mind it'll be low because we're only at around 60 volts AC, and we're running 11.1 and 16.8, which should be what, 28 milliamps of current. Let's look at what our meter says, and it is kind of hard to read. A little below 30. So it looks like our milliamp plate current meter is working beautifully. The plate voltage readings around 263, and I'm only seeing around 200 here on my plate voltage meter. We'll have to keep an eye on that, see if we can figure that out. Let's crank up the power supply with our variac to around 100 volts AC. As you can see, I've cranked it up quite a bit higher, and we're right at the correct value here, about 200 volts on our 12AX7 plate, and we're a little over the 227. Remember, we wanted 220 on our output tube screen, and let's see, we're up to 285 on our plate voltage. And lo and behold, once I cranked up the plate voltage higher than 60, the meter started being a whole lot more accurate. In fact, that looks like around 285 to me, so that's really sweet. Okay, so the meters are working well. And I don't want to crank it up much higher than this because I don't want to exceed the parameters for the 12AX7. So, I think next what I'll do is put in a GZ34 rectifier tube back there and a pair of 6L6GCs, and we'll start over again and crank up our voltage and see if we need to correct some of our voltage dropping resistance, and to get our optimum plate dissipation on our 6L6s, and then we'll move on to the KT-88. I think this would probably be a perfect place to end part 2 in our video series. We know that our amp is functioning actually quite well and very quietly, that our voltages are in the ballpark and probably will take a little fine-tuning. But at this point, we know that we have a fully functional, single-ended, relatively high wattage circuit here. And in part 3, we'll finish all the fine-tuning, and we'll go into some testing and comparing of both the 6L6 parallel pair and the KT-88 single output tube. You might have gotten a glimpse of the bandage on my left hand. I had surgery for pinched nerves. I've had a lot of numbness. I was losing control of actually both hands. I'm going to have the surgery done on my right hand in another week. Okay, hopefully that will not interfere too much with the preparation of the part 3 video. I still have the use of my fingers, and so far everything's going quite well. So I just thought I'd let you know why you were seeing that odd bandage on my left hand. As usual, I'd like to take a few moments to thank all my Patreon patrons and PayPal contributors for keeping us on the air and advertising free for another month. If you'd like to join them in supporting our channel, I will put links in the video description which will enable you to do so. I hope you've enjoyed part 2 of this video series and that you'll stay tuned. And I'm going to say probably about 30 days or so for the part 3 video to be posted. As usual, I'll post it first for my Patreon patrons, and then a week or so later for the general YouTube audience. Meanwhile, thank you so much for tuning in and spending your time with us in our electronic endeavors. I hope you've enjoyed what you've seen, and we'll stay tuned for our future releases. Until then, bye for now.